Okay, today we're moving on in stoichiometry and starting to introduce what a chemical equation is. All right, this is kind of like a math equation where you take like an English sentence, 2 plus 1 equals 3. All right, you can write it out in words or you can write it out in like the number 2 plus the number 1 equals the number 3. Chemical equations, you're going to get formulas or compounds or elements. They're going to react and produce products. So we're going to talk about that and how we do that. And then we have to balance them, which the only way you're going to get balancing is practicing. And this is the part that's going to be on you on your own. Okay, first things first, bell ringer. How many grams is 0.36 moles of potassium permanganate? All right, this is obviously going to be the bell ringer question. I'm actually going to probably put two questions on the Edpuzzle. First, going to ask you what is the formula for potassium permanganate, and then going to ask you this question: how many moles does it have? So first of all, the formula for potassium permanganate is KMnO4. Okay. You got a crisscross jump. Permanganate is a polyatomic ion, which is on table E. -1 ion. Potassium is a +1 ion, so they cross out the ones and you get KMnO4. All right. You then need the GFM to figure this out. So when you add up 1 potassium, 1 manganese, and 4 oxygens, you get 158.0 grams per mole. And you got to divide the 0.36 by 158.0. When you do that, you get a number that's pretty small. Do not put it as 0.002. All right, that's not enough digits. You need to have probably at least 3. So 0.00, which those are place value zeros, those don't count, but you still need them. So 0.00228 would be the grams. Actually, I did that backwards. I did that as grams and going to moles. Let me do it right now. So it's 0.36, my bad, 0.36 times 158. So that's 56.9 grams. Okay, so 56.9 grams is the answer there. Okay, all right, we're gonna move on. So chemical equations, you know, some people like the history part of this. All right, this can be accredited to a scientist called Antoine Lavoisier back in the late 1800s or 1700s. And it talks about equations having reactants turning into products. So what we're going to see is that anything on the left side of the arrow is going to be considered a reactant. Sometimes we have 1, sometimes we have 2, sometimes we have 17 reactants, and then they can turn into an X number of products. All right. It doesn't matter that how many different products there are. What matters is that the masses are conserved. And we'll talk about that because we have to uphold the law of conservation of matter. Anything that's conserving. So in chemistry, we can talk about the law of conservation of energy, law of conservation of matter, the law of conservation of charge. All of those things that we were talking about conserving means that they're not gaining or losing. All right, they are conserved. They stay the same. So in a chemical reaction, because we're talking about matter, the matter or the mass has to stay the same. So the mass of the reactants must add up to equal the mass of the products. You can't lose products. You can't lose mass, which means you've lost products. You can't gain mass, which means you would gain products. They have to stay the same. All right. And this works out really well for us because it allows us to figure out some things, whether it's in terms of grams or moles. All right. Law of conservation of matter states that matter cannot be gained or lost. All right. It's got to be conserved. All right. This is why we have to quote unquote balance equations, is to uphold the law of conservation of matter. We're going to learn today how to balance those equations. We'll probably give you some more easier ones today, and we can progress to some challenging ones. All right, but what that means is in terms of matter, you got to have the same number of atoms on the left as there are on the right. All right. So, you know, the same number of oxygen atoms you start with, you got to finish with the same number of oxygen atoms. Same number of hydrogen atoms on the left, you got to finish with the same number of hydrogen atoms on the right, which is also going to mean the mass of those atoms are going to be the same on the left and right as well. Okay. Now, one thing we didn't talk about, we'll talk about later in the year, is sometimes reactions can go backwards. They can go from what we would call products to reactants. It's really not products to reactants, but it can go from the right side of the reaction to the left side of the reaction. So in the dividing line in the reaction is always this arrow. You always have to find that arrow in the reaction, okay? All right, so down here, we've got a reaction where we've got diatomic hydrogen reacting with diatomic oxygen to make water. All right, this is a reaction that happens all the time. But as written, it does not uphold the law of conservation of matter. Because if we look here, I'm trying not to go down there. And you'll just look below the dot, I guess. You've got two hydrogens here, and over here you've got two hydrogens, which is good. Those equal each other, so they haven't been gained or lost. All right, if we look here, now our arrow's at this spot right here. If we look down below here, we've got two oxygen atoms, but we finished with one oxygen atom. So we can't do that. All right, this reaction as written is not upholding the law of conservation of matter. So we have to put what are called coefficients. If you remember from math, coefficients are the numbers that we write in front of things to represent more of them. So to balance this one, I'm not going to go through the balancing of it. We would have to add a 2 in front of the water, because what that does is that gives us, I'm trying to find the spot where I can't go below. It's right about here. This means this 2 would distribute to the oxygen, so we have 2 oxygens. All right, we look back at the reactant side, we have 2 oxygens written with the O subscript 2, so that's the same thing, same number. Over here, we've got 4 hydrogens now, because we put a 2 in front of it. So now over here, we have to have 4 hydrogens. That's why we had to add a 2 over here. Now, the question that comes up that confuses people all the time is when the equation is properly balanced, like the one is written here, what is the sum of the coefficients? So sum just means adding. Coefficients means add up all of the coefficients. So you have a 2 here, you have a 2 here, which some people would jump at the answer 4. Realistically, it's 5 because there's a 1 here. We don't write the 1 because it's redundant, but there is a 5 here, or a 1 here. So that means the sum of the coefficients is going to be 5 in this case. All right, and that's pretty much what we're going to spend our time doing today, is giving you reactions and learning how to balance them. As we get through this unit, you'll be able to write the reactions, but we're not there as of yet. Okay, so chemical equations, like we saw before, will represent the kind of reactants and products and the relative amounts in the reaction. So if I look back here, you look down at that bottom reaction, you've got the 2 hydrogen molecules as written, plus 1 oxygen molecule makes 2 molecules of water. Okay. So here we go. So we got this reaction right here. So here we've got aluminum reacts with oxygen to make aluminum oxide. Okay. Now, if we look here, it's not balanced. All right. We've got 1 aluminum here. We've got 2 aluminums there. We've got 2 oxygens here. We've got 3 oxygens there. So these are not balanced in any way, shape, or form. All right. So you have to try to balance them. There's no right or wrong way to do this. I will tell you, oxygen and hydrogens, you're going to want to leave to last because they usually will shake out, shall we say. All right. And do your other non-oxygen, non-hydrogen atoms first. So in this case here, we have 1 aluminum here, 2 aluminums here. So to balance this, we have to put a 2 in front of the aluminum over here. So these numbers that we're going to put in front are called coefficients. All right. And I don't remember how I timed this. Let me see if I did. All right, so I just did the final balancing of it, so we're not going to worry about this right now. So these numbers right here, when this is ultimately balanced, you're going to end up with these coefficients. You're going to end up with 4 in front of aluminum. We look over here, we have 4 aluminums. You have 6 oxygens here. You have 2 times 3, 6 oxygens here. So this is ultimately balanced. We didn't go through how to balance it, and that's fine. I didn't think I did it on this one. All right, just showing you that these purple or these light purple colored numbers are coefficients. That's all we can add to balance it, and the coefficients have to be a whole number. You can't put a fraction or a decimal point in there, just like we can't write a fraction or a decimal point down in here as a subscript. They have to be some whole number, okay? All right, so how do we do these? Or what does these mean? So this is kind of a pictorial representation of it. Sometimes it works for people. All right, so if you looked at, like, a C means that there's 1 carbon atom, and O means there's 1 oxygen atom. Now, if you look here, O2 means that there's a bond. So there's two O's connected. So this means a molecule of oxygen. Here you got CO. So this means there's a bond between the carbon and oxygen, and we have 1 molecule of it. All right, or if it's an ionic compound, you have 1 particle of it. Now, CO2 means the particle has 2 oxygens and 1 carbon, so that's why you get a structure that looks like this. All right, but combined, this is 1 molecule. That's why there's a 1 coefficient in front of it. You look down here, you've got carbon dioxide particle, but now we have a 3 coefficient in front of it. So that's why we have 3 of them. But if we look at this and count up the numbers of atoms, if we look here, we've got 3 carbons and we count 1, 2, 3. But here it's 3 times 2 oxygens for a total of 6. So we get 1, 2, 3, 4, 5, 6 oxygens. So these 3's distribute out. All right, the subscripts tell you how many atoms of a particular element are in a compound. The coefficient tells you about the quantity. So the subscripts here can tell you, how many atoms you have of that. And then the coefficients only come about when you're balancing equations. The only time you're going to deal with coefficients in there. So that's why we do it this way. So this is just a way to kind of, sometimes people like to see the visual rep of it. And then we're going to go through some balancing right here. So here we go. Here's our first reaction to balance. So there's a picture up here. You've got aluminum and bromine. You got aluminum here. You got bromine gas here. And then you're going to mix them together. I don't have a final reaction of it because we're really not allowed to have bromine in school. So I can't take a picture of that or a video of that. But anyways, we're going to look here. Now the S, the L, and the S doesn't mean anything in terms of balancing. I just put it there because it's extra information and you will sometimes see it. S means solid. L means liquid. S means solid. If we look here, we got 1 aluminum atom. Here's our arrow, or our arrow, and turning into 1 aluminum atom. So we're good there. The aluminums are currently balanced. We look at my bromines. I've got 2 bromines, and I've got 3 bromines. Those are not equal to each other. So to balance these, we have to find what's called like a lowest common multiple of them. All right, and the lowest common multiple of 2 and 3 would be 6. So you got to get this to 6, we would have to put a 3 in front of it. So this is what it looks like. This means 1 aluminum atom. This means Br2. This is 1 bromine molecule. And then we've got 1 AlBr3. So this is kind of pictorially what it looks like. Some people like the pictures part of it. But you can see we have 2 blue spheres and we have 3 blue spheres over here. So they're not equal to each other. So we have to get to the lowest common multiple, which is 6. So we're going to put a 3 here, which means now I have 3 of these particles, which means I have 6 total atoms of bromine. How do I get bromine on this side to 6? We would put a 2 there. So here we got the 3 here. And then to get this side to 6, we have to put a 2 here, which means we're going to add another particle of this. So now we count up, we got 6 blues on the left. We got 6 blues on the right. But now if we notice what happened, we have 2 green ones. We have 2 aluminums here, but we only start off with 1 of them. So to balance this, we have to put a 2 in front over here, and then you end up with the second aluminum atom here. So you can do it kind of pictorially. You can do it with the numbers. Ultimately, you just go back and forth. Some of the coefficients when this equation is properly balanced is 2 plus 3 is 5 plus 2 is 7. Okay? All right. Moving on. So here we go. So I've got this. Now this reaction is different. All right, this is using aluminum and oxygen. This one up here used aluminum and bromine. There's all different kinds of things we can do here. All right, so first things first, see if it's balanced. 1 aluminum, 2 aluminums. It's not balanced. We have 2 oxygens. 2 oxygens, those are balanced, so that's good. The oxygens are balanced, but they might not stay that way. So to balance the aluminums, I can't do anything over here because I already have 2 here. This I only have 1, so what I can do is I can just add a 2 here to the aluminum. Now I have 2 aluminums. 2 aluminums, I have 2 oxygens and 2 oxygens. So I'm good. All right, some of the coefficients here, and I'm always going to ask this just to kind of reinforce it. 2 plus 1 plus 1, which is 4. Okay, now this one, we've got iron plus chlorine makes iron 3 chloride. It's got a Roman numeral 3 because iron's a transition metal. I'm going to try to talk through some of these things that we don't get an opportunity to do in class. All right, but you got to balance it if it's not balanced. All right, so if I look here, I've got 1 iron and 1 iron. I got 2 chlorines and 3 chlorines. So the irons are balanced. I don't have any oxygens or hydrogens here, so I can ignore those. But now here, I've got 2 chlorines and 3 chlorines, like we saw in the previous one. The lowest common multiple of 2 and 3 is 6. So I've got to get one of these to 6. So I'm going to get I believe I put the chlorines to 6 first. All right, so I got 3 chlorines here, or 6 total chlorines here, 3 molecules of chlorine. All right, to get this to 6 over here, I have to put a 2 in front of here, which gives me 6 chlorines over here. Now, I did change the irons though. Now I have 2 irons that I'm finishing with. So to get 2 irons that I start with, I have to put a 2 over there. And then the sum of the coefficients is 2, 3, 2. An easy way, like when we're doing stuff and we're balancing them, sometimes when I check them, I'll say, what is the coefficients from left to right? For this reaction, it would be 2, 3, 2. For this reaction, it would be 2, 1, 1. All right, it's just so that we can, you don't have to write out the whole thing. And when we get to the Edpuzzles, I'll probably have you guys do that as well. You know, what are the coefficients for all the things from left to right? And you would just, for this reaction, you would say 2, 3, 2. Okay, now we go on to this reaction. Oh boy, it looks really big, looks really confusing, looks really complicated. It's really not all that bad. These are the things that just listening to me and taking a screenshot of it is not going to help you. You have to probably write it down, pause the video, and then try to do it. And then listen to my explanation afterwards, because that's what I would do in class. I would say, all right, here's this reaction, try to balance it. Okay, but I'm not going to do the wait time on the video, so the video is not super long in here. Okay, all right, so what I recommend is leaving oxygen and hydrogens to the last, because those usually, it makes life easier. Not always, but usually it does. So start with your non-hydrogen and your non-oxygens. So iron, you've got 2 here. Iron, you've got 2 here. So currently the irons are balanced. We're good. All right, sulfurs. You got 1 sulfur here, because this 4 only goes to that O, and this 2 goes to that hydrogen. So sulfurs, we have 1. Here, we have 3 sulfurs, because this 3 out here will distribute into this sulfur. So we got 3 that we finish with. Here's our arrow. So we got to put a 3 over here to get the sulfurs equal to each other. All right. So now our sulfurs are good. Now our irons are good. Okay. I honestly don't remember if I did hydrogens or oxygens next. I'm going to guess I did hydrogens, because if I look here, I've got hydrogen in 1 spot, 2 spots. If I look at oxygens, I've got them in 1, 2, 3, 4 spots. Okay, so always go to the one that's in the least number of spots. It's the easiest to balance usually. So here I've got 6 hydrogens. I got to get this to 6, so I'm going to put a 3 in front of here. Hopefully I did. Woohoo, I remembered. All right, so we got 6 hydrogens we start with, 6 hydrogens we finish with. Now we have our oxygens. Hopefully the oxygens just work themselves out. So if I look here, I've got 3 oxygens in Fe2O3. I've got 12 oxygens in H2SO4. So 3 plus 12 is 15 on the left side. Over here, I've got 12 oxygens here and 3 oxygens here for a total of 15. Sweet. All right, if I were to ask you for the coefficients in this equation, you would write 1, 3, 1, 3. Or the sum of the coefficients is 8, because you got 4 on the left, 4 on the right. All right, let's try another one. So here we got potassium chlorate decomposing into potassium chloride and oxygen. Okay, first things first, do the non-oxygen hydrogens first. So we look at potassium, we got 1 potassium, we're good. We got 1 chlorine, we're good. Now I'd recommend pausing this and you trying to balancing it from here so that you can get the practice that you need. We got 3 oxygens, 2 oxygens. So the lowest common multiple of 3 and 2, we got to put a 2 in front of this one over here to get to 6 oxygens, which means we're gonna have to put a 3 in front of over here to get this one to 6 oxygens. All right, and now what we did change though is we did change our numbers of potassiums and chlorines. We got 2 of them now, so we got to put a 2 there. So our sum of the coefficients in this case would be 2 plus 2 plus 3, which is 7. If we were to write out just the coefficients, it would be 2, 2, 3. Okay, now at this point, you must practice. All right, you will not get balancing equations if you just turn this off and walk away from it. All right, so make sure you do the practice that's been assigned to you.